marching along with series, and for some reason my display. The first coach we met was the nth term test, right? And what was kind of the attitude of the nth term test?
Discrete divergence,
Yeah, it's going to be kind of mean, going to be like very negative. It'll only tell you one thing. The nth term test will say the series diverges, and if the series might converge, it's not going to say anything. It's going to be very uninformative. And so if a series like survives the nth term test, then you just keep moving on, right? So survives mean it didn't say stop, you diverge. It didn't really say much of anything. In cases like that, we just keep marching on to some other tests, okay? And we're going to look at some of those today. What was the other coach that we met, the other test that we met? Geometric series, that's right, geometric series test. So geometric series test really only applies specifically to geometric series. So the key to using that is identifying what a geometric series is. Do you guys remember what identifies a geometric series?
common ratio.
Okay, so a common ratio, but then take a step back. How would you even know to think to look for a common ratio?
A number to an exponent.
Yeah, a number to what kind of exponent?
A variable.
Variable, yeah. So if your base is numerical, like 5 or 6 or 3, and your exponent, like she said, is a variable, that's an indicator that you've got a geometric series. So the geometric series test only applies to geometric series. So it's like a very specialized coach, right? So if you think about some of the coaches you might have had in the past, you could have a football coach that feels kind of specialized, but then you could have a running backs coach, right? That could be even more specialized. You could have a swimming coach, that's one thing, but then you could also have a diving coach, would be even more specialized than just swimming. And maybe there's even a 5-meter platform coach and a springboard coach, and you could get more and more specialized. Geometric series test is very specialized. It only applies to one type of thing, and that's the geometric series. Geometric series test is very balanced though, right? It'll say convergence or divergence. It's not going to be silent on either of those. That make sense? Okay. So today we're going to meet 2 more of these tests, 2 more of these coaches, and you're going to find that both of these coaches, if you will, are both balanced. They're both going to give both sides of information, and it's the integral test and the p-test. So let's take a look at the integral test first, and we will explore a little bit with why this works, and if I feel like we have time, we might do a little proof that might help you understand a little bit more about the integral test. Okay, so the integral test. There we go. It says if f is positive, continuous, and decreasing. So those are the conditions for this integral test. So, so this function f has to be above the x-axis, right? And it has to be continuous, and it has to be decreasing on whatever interval we happen to be looking at. I apologize, I don't know what the deal with the internet is. I've been having issues all morning, even with my computer. I don't know what the deal with that is, but hopefully it'll be okay. All right, so then there's a big jump here, right? So f is this function. It's positive, continuous, and decreasing. And this is an important point right here. And if the nth term of the series is the same as f of n. So as you think about some of the nth terms of series we looked at, they do look like functions, don't they? And so if the nth term is equivalent to this f of n function, then the series, which is on the left, and the integral, the improper integral, which is on the right, both of those are going to converge, or both of those will diverge. But typically, or I'd say pretty much always, they won't converge to the same value if they do converge. So basically, the basic plot here is we can use an integral to help inform us about a series. Okay, so if you've got some series, a sub n, whatever it happens to be, if it is of a convenient form, then we could use an integral to tell us about the convergence or divergence of this. Okay? Again, the conditions are f has to be positive, continuous, and decreasing, and the nth term has to match the function. Okay, so we can run an indefinite, or not indefinite, an improper integral on it and draw a conclusion based on that. Okay, so there's definitely, I would think that there would be some pretty big question marks as to why does that work and how does that work, and I'll try to answer those as we go along. And like I said, I think if we have time, which we might, I'd like to do a proof either today or tomorrow of that. Okay, so then the other test we're going to look at here is the p-series, and we're going to look at a specific version of that as well called the harmonic series. But the P series is the same thing we looked at way back in like November or whenever that was when we looked at improper integrals. Remember that? We looked at the p-test. So this is it again. So a p-series is specifically of this form, and I don't know why that's highlighted in blue, and I don't know why the whole screen just went away. Now it's back. So anyways, I don't know why that's highlighted in blue. There's no particular reason for that. So p-series is a very specific form, and it is this sigma from 1 to infinity or whatever to infinity. But then the thing that's very specific, it is 1 over n to the p. 1 over n to the p. So it's a very narrow definition, okay? Kind of like the geometric series is a very specific thing. The p series is very specific as well. So if you've got 1 over n to the p, then that's what we call a p series, and really it's going to come down to what is the value of p, okay? So let's go and look down here at the p-test. We'll come back up and talk about the harmonic series. So the p series converges if p is bigger than 1. So if you've got 1 over, so some examples, if you've got sigma of 1 over n squared, p is bigger than 1. So that series would converge. If you've got 1 over n cubed, that p-value is bigger than 1, so that series would converge. If you've got 1 over n to the 2.6, 2.6 is bigger than 1, so that series would converge. As soon as that p-value drops between 0 and 1, so something like 1/2 for an exponent, now that p-value is between 0 and 1, including 1 potentially, and so that series would diverge. That's what you see from the p-test down below. So some things that are not the p-test that are going to look like the p-test, we're going to have to use different things to handle these, would be stuff like sigma of 1 over n cubed plus n. It's not a p-series because of the plus n. Or if you had n cubed minus 9, not a p-series because of the minus 9. There's ways to deal with this, but it's not a p-series. Does that make sense? And the p-test is really cool because all you got to do is look at one number and you're like, done, right? But the temptation then is to try to see everything as being a p-series when everything is not necessarily a p-series. In fact, many things aren't. And so it's important to realize where this does apply and where this does not apply. So we'll practice all this here in a second. I also wanted to mention this harmonic series thing, and the harmonic series is used a lot. So a harmonic series is simply a specific form of the p series when p is 1. Okay, so when p is 1, then we call this the harmonic series. We'll talk a little bit about the convergence or divergence of that here in a second. This is the classic harmonic series over here, sigma of 1 over n equals 1 plus 1/2 plus 1/3 plus 1/4 ... And I want to kind of go back a little bit. Do you guys remember way back we first started looking at the nth term test? And we were looking at sequences and series. In fact, let me draw this on the board, I guess. Remember how we were looking at sequences and I said if we had a graph of a sequence and the sequence did this, like the terms of the sequence did this, and this was like a 4. Do you remember how we looked at that and we said, hey, if this was a series where we were adding, this plus this plus this plus this, ... would this series converge? And do you guys remember what you said? Would this series converge? Not the sequence. The sequence clearly converges, at least the way I've drawn it here, towards 4, right? But would the series converge? No, it would not, because isn't the series simply a summation of all the terms in the sequence? So the series would be this plus this plus this plus this plus this plus this, and at the end wouldn't essentially you just be doing plus 4, plus 4, plus 4, right? I mean, be like slightly bigger than 4 plus a little bit less than that, but still bigger than 4. So in the end, you'd just be doing essentially plus 4 forever. So isn't that going to end up being an infinite expression? It's going to be heading towards infinity. But then the other question I said was, what if you had this where the terms in your sequence started here and then here and did this, and it appears that the terms in the sequence are heading towards 0. I mean, that's what I'm trying to represent there. So if that were a series and you were actually adding up all those individual terms and the individual terms were heading towards 0, I said, do you think that that would converge or diverge as a series? And do you remember what you said? The answer was maybe. The answer was maybe. And the caveat with the maybe is, how fast do they approach 0? Okay? And so let's come back around to that idea here, because if you take a look at the harmonic series, and I'm just going to do the real generic form, or the real basic form of the harmonic series. So if I had sigma from n equals 1 to infinity of 1 over n, and I was looking at that and just saying, all right, does that converge to a real number, or does that diverge towards infinity? So I guess I could approach it from a couple of places. I could look at this as a p-series, I suppose, but I could look at it like this. What if I just said, let's do an nth term test. Say limit as n goes towards infinity of the nth term. So limit as n goes to infinity of 1 over n, and I would get 0, right? Because as the denominator gets huge and the numerator is held constant at 1, then the overall value of the fraction is heading towards 0. And so it would be really tempting to look at this and be like, look, the nth term is heading towards 0, therefore the series must converge. But it doesn't. We're going to find out it doesn't. We could actually simplify this significantly and be like, hey, it's technically a p-series, and p is 1, right? And according to the p-test down here, if p is 0 to 1, including 1, the series diverges. We're going to kind of explore a little bit why that is here in a second. Some books, your textbook included, say that a general form of the harmonic series is this, 1 over an plus b. So they allow for a constant to be added on to the harmonic piece of the denominator. Other textbooks are not so liberal with that, so just know that there could be some disagreement. Later on, if you took some class on series, they might not be that liberal with that. Okay? But we'll still use that for sure. Okay. Any questions at all? Yes, sir.
Doesn't the p-test tell you if you're pregnant or not?
Tell you if you're what? Pregnant or not? Well, depending on if you're female or male. And that is legit, yes. For those that didn't know, if you think you might be pregnant or you think your spouse would be pregnant perhaps, all you have to do is pee on a special stick. And the stick will tell you, yes, you are, or no, you are not.
Bang stick?
Special stick, I said. I didn't say any stick. It's a very special stick that you buy at like Walgreens or King Soopers or something. And yeah,
I'll try it out.
pretty cool deal. If you get to be a parent someday, that moment of like looking at the special stick and seeing the symbol that says pregnant, whoa, it's really exciting. It is. It is. I'll never forget. When I found out my wife was pregnant with her first child, never forget where I was, what I was eating, because I was eating lunch, and she like goes off to the bathroom and comes back, and I was like, whoa. And didn't really finish my lunch. What's that?
What were you eating?
You know what? I was eating noodles and company. I was eating pesto cavatappi that I had brought home. I hardly ever eat there, but I just had bought it on the way home, and yeah, I don't think I finished it. We were just so excited. Yeah. All right. So I don't know how we got onto that, other than the fact that the p-test could have multiple meanings. So let's take a look at number 1, and there we go. I want that. So number 1 says, use an appropriate test to determine convergence or divergence, and that's vague, right? Sometimes we'll be really specific, and I'm going to say, please use this test, because I just want to see if you can use it, because there might be other ways you can kind of skirt around the thing that I want to assess you on. But here, this is just really vague. Use the appropriate test. So maybe you'd run through some ideas. I think the first thing you should always consider is the nth term test. And maybe don't write this one down, maybe just watch this. You might consider this and say, all right, limit as n goes to infinity of the nth term. And of course, if you did this, you'd end up with a L'Hopital thing, wouldn't you? L'Hopital expression. I'm telling you, you don't really need to do this. So then maybe you do a L'Hopital thing and say, oops, let's put an arrow there. Let's not break my own rule. So that's an arrow. Limit as n goes to infinity, and you'd say 1 over 2n. And you could say, hey, look, now the denominator is getting gigantic, the numerator is held constant. So this is heading towards 0 for a limit. So what does the nth term test tell us on this one? Say again?
It doesn't.
What does the nth term tell us?
It doesn't.
Remember the nth term test, yeah, the nth term, no, it doesn't even tell us, it doesn't tell us that it doesn't diverge either. It says nothing.
Yeah.
It says, so the correct answer to my question of what does the nth term tell us? It tells us nothing. It tells us absolutely nothing. Since we did our nth term test and we got 0, then it just tells us absolutely nothing. We might be heading towards divergence. We might be heading towards convergence. We really, at this point, have no idea. So the nth term test was extremely unhelpful, and so we're not going to be too concerned about that. I am, however, concerned that there we go. And so we move on. And so maybe we think about the geometric series test. So we look at this and say, hey, let's use the geometric series test because I know how to do that. This has to be a geometric series in order for us to do that. And it's not because we have variable bases and numerical exponents, making it sort of the opposite of the geometric pattern that we'd be looking for here. So we can't use a geometric series test. And so the newest ones we learned were the p-test and the integral test. So you look at this and say, is this a p-test?
No.
It's not, because the numerator is a variable and the denominator has that +1 hanging on there. The only other option we have at this point, there will be other options later, the only other option we have is the integral test. So here's how we do the integral test. We're going to set up an integral such that the nth term is our integrand. And we're going to match the limits of integration there. So it's going to be integral from 1 to infinity of n over n squared plus 1 dn. And so like I told you before, there is a fairly easy proof to this, and I'd love to show it to you either today or tomorrow. I can't decide what it's going to be. To show that this works. But we got to consider the conditions. So the conditions for the integral test are the function, the nth term here, has to be positive on the interval, it has to be continuous on the interval, and it has to show a decreasing pattern on the interval. Okay? So there's a number of ways to arrive at that. You could potentially look at a graph for this and see the decreasing nature of this, right? You could also see the positive nature of this on a graph as well as the continuity. I think we could do some of that for sure without a graph or a calculator. Think about the inputs. The inputs are all going to be positive, aren't they? 1, 2, 3, 4, 5, dot, dot, dot. So the numerator is always going to be positive. N squared guarantees positivity. Plus 1 just makes it even that much more positive. And so we know for sure that, let's see here, we could say something like f of n equals n over n squared plus 1 is positive. We know that for sure based on the analysis we just did. Continuous. Is it continuous? Continuity meaning there's no removable discontinuities, there's no vertical asymptotes, no jumps. There's no jumps because it's not piecewise, right? Or a greatest integer function or something like that. Are there any vertical asymptotes on our interval? N squared plus 1 doesn't have any zeros, does it? So there's really not even a possibility of that. So I'd say yes, for sure, continuous. And then decreasing, I suppose a way you could think about decreasing here is as n gets bigger from 1, 2, 3, 4, 5, the denominator is a squared degree, the numerator is a first degree, and so I think we could clearly see a decreasing pattern at least at some point. So I think we can say positive, continuous, and decreasing on the interval 1 to infinity. And basically those are just the conditions for us to be able to use this integral test. Yes, ma'am?
So you wouldn't need to find the derivatives or anything to prove it's decreasing?
Right. Yeah. So typically not, unless unless it gave really specific instructions. Like if you can just look at a graph or see a pattern and say, "Hey, I see these conditions were met," that's going to be good enough for us. Yes, ma'am.
So points wise on a test or the AP test, do you have to say all those things?
Yeah. So if it were a question like this where it's just totally open and it says use some test and it doesn't specify anything, you need to justify why you use this test.
Okay.
Right? So if this were a geometric series, you'd have to say, hey, this is a geometric series, so I'm going to use the geometric series test, and here's the common ratio. And yeah, so based on the way this question is worded, I would say, yeah, you would need to do that for sure. And the conditions are certainly important. I would say the conditions would be something that could be tested as well or assessed as well. Like, hey, somebody used the integral test. Was it appropriate for them to do that, and why? Like that kind of thing. Okay, so when you're working on an improper integral, you've got to do the limit as maybe like b goes to infinity, integral from 1 to b. Don't forget that you've got to include that limit because it is an improper integral.
Can you put the B thing in after we evaluate the other one?
Yeah, you just could do that at some point, but it has to be a limit.
Yep.
A limit has to be, but it could be, the timing could be a little different. Yep. Okay, so let's see how good you guys are with remembering kind of like first semester integral, integrand forms. So any ideas what this integrand leads to when you actually do the integral? It's integral, but we're off by a factor of 2. Yep. So we go times 2 and times 1/2. You guys identified natural log correctly. That's great. And so it'd be the limit as b goes to infinity of 1/2 natural log, absolute value n squared plus 1. We're evaluating from 1 to b. Okay, so we do a little more work here with FTC, and let's see, we come up here and do that. So it'd be limit as b heads towards infinity, and it would be 1/2 ln of b squared plus 1 minus 1/2 ln of 2. Do all that arithmetic right, I think? Okay. So, then we've got to think about what this limit is actually going to do. So the limit obviously has no effect whatsoever on that term. There's no b's in there. But it'll obviously have an effect on the first term. So as b gets really, really huge, what's going to happen with that ln of b squared plus 1? Heading towards what? Slowly, but towards infinity, right? If you think about, I'll erase this, but if you think about the graph of natural log, just the real basic natural log graph, that's maybe too extreme. It does something like that, doesn't it? As you head off way towards the right edge of the graph, which is what we're talking about, it does want to kind of flatten out a little bit, but it never actually does flatten out, right? It keeps increasing at a decreasing rate, but it does keep increasing. So as b gets huge, ln of b squared plus 1 gets huge as well. And so we could say then, and of course 1/2 of a huge number is just a similarly huge concept as far as the number goes. So we'd be looking at this. That minus 1/2 ln of 2 is still infinity. Make sense? All right, so then the conclusion we get here is this. So the integral we found diverges, right? So we could say, well, really, we've set this up pretty well. So I think we could just say essentially this. Therefore, the original series, integral from, or not integral, sigma from 1 to infinity of n over n squared plus 1 also diverges. And the reasoning there, of course, is the integral, or the name of our reasoning pattern there is the integral test. And so I'm going to ask, for the most part on your quizzes and tests, I'm going to actually ask you in the question, I'm going to say, use your reasoning, come up with convergence or divergence, but not only give good reasoning, but please name the thing you used, right? It won't always be a required thing, say like an AP test, but at this early stage, I want to know, like, I think I'm using the integral test. And if I look at your reasoning, I'm like, that's not the integral test, that's a geometric series test. I want to be able to point that out to you and say, use some good reasoning, but you're calling it the wrong thing, and so you might end up misapplying it at some point. So just, be careful. Okay, so does that make sense? I tried to take you through that journey of, hey, this is a question. Should I use the nth term test? Nope, doesn't really tell us anything. Geometric series? Nope, because it's not a geometric series. It's not a p-series either, so you can't use the p-test. We ended up using the integral test. Any questions at all? Okay. Let's then take a look at the one we looked at earlier. And I guess let's one specific instruction for number 2. So number 2 is a p-series, right? And what's the p-value for number 2? It's 1 over n to the 1, right? So p is 1. And so you could, like, if I don't think I'd ever ask you this question on a quiz or test because I'm going to consider it to be so fundamental that we'd probably reason off of it instead of just like having this be the thing. But you could look at this and say, hey, look, p is 1, and according to the p-test, this series diverges. So we know right off the bat this series diverges. But this is that one question that we looked at earlier, where if I did do an nth term test, please don't write this down. If I did do that nth term test here, 1 over n, I get 0 again, right? Kind of like we did before. But we know that this series diverges, and so the thought would then be, how could we prove this? How could we prove that this basic harmonic series, right, which is what this is, diverges? And so to do this, I would say we could look at an integral test. Okay, so this would be an opportunity for you guys to try to work on the mechanics of an integral test. Again, we just did this. See if you can do it again now. See if you can do it on your own. So take a look at number 2, using the integral test. I know you could definitely use the p-test. And if it were a quiz, you'd be foolish to not use the p-test. But use the integral test here just for the practice that we maybe would want with that. Okay, so running through really the options here. This is going to, like I said before, the nth term test is going to say nothing here. This is not a geometric series, so you can't use the GST. It is a p-series, so you could have used that, but I asked you to use the integral test, and so here's what it would look like. You'd want to say that f of n equals 1 over n
It's frozen.
is, thank you, is positive, continuous, and decreasing on our interval. So again, if you can just recognize it, you don't have to go through and prove every piece of that, or any piece of that, to be honest. You just need to recognize that those are the conditions, and that those conditions have been met. Okay, so therefore we can use the integral test. So we could say something like limit as b goes to infinity of the integral from 1 to b of 1 over n dn is the item we're going to try to evaluate. So this would be limit as b goes towards infinity of natural log of n evaluated from 1 to b. And if we continue on, we can see that it's limit as b goes to infinity of natural log of b minus natural log of 1. And just a side note, what's the natural log of 1? 0. Okay, so it's not like the limit applied to that anyways, but it is a 0. So then as b gets huge, what is ln of b tending towards? Similar to what we did earlier, yeah, heading towards infinity. So we, based on our setup here, the fact that we put out the conditions, we can use the integral test. Because that is infinity, we can say, therefore, the original series, sigma from 1 to infinity of 1 over n, also diverges. And we use the integral test for that. Okay, any questions? That flow okay for you? Can you see how the key to these is going to be identify the most appropriate, efficient test to use? That's going to be the key. You can get all these tests down. We have a few more to go. But being able to say it's this or it's that, or this would be the best way. I'm going to show you some other ways that might be the best way, even with some of these. All right, so there's no questions? Yes, McKenna.
So on the other page, it says either both converge or both diverge, but not necessarily to the same value. So what is that?
Let's do another one, and I'll illustrate that for you. Yep, that's a good question. So let's see here. Would three would be a good one. To answer your question, I think 3 would be a real good one. I'll tell you what. Let's mix it up a tiny bit. Can we do number 4? Because number 4 is real quick, and we'll come back to number 3. We'll finish our class with number 3. Okay, so number 4. Again, I think I'll try to take you through the reasoning that you might experience if you're doing a quiz or a test. You'd maybe look at number 4 and say, all right, what does the nth term test tell me? So if you think, you could just do this in your head. You could say limit as n goes to infinity of that nth term. What are we going to get? 0, right? Because the top's going to get huge. Numerator's held constant, the denominator's going to get huge. The top is held constant at 1. We're heading towards 0. So the nth term test tells us what? Nothing. Yes, the only thing it'll tell us is diverges. It won't tell us anything other than that. Okay, so since the nth term test was not informative at all, then you think about the geometric series test, right? Is that a geometric series? No, you got the variable base with the numerical exponent, so it's not a geometric series, so you can't use the GST. Is this a p-series? Yes, it is a p-series. It just has to be 1 over a variable to the some numerical exponent, and that makes it a p-series. And so what you'd want to do then, based on the fact that this is a p-series, you could maybe just say is a p-series, and p is equal to what? 4/3. And what is so special about 4/3? How's that going to help us?
Greater than 1.
Yeah, and I want to be specific here. It's greater than or equal to 1. It is greater than 1. That's not wrong. But if that p-value was 1, it would be a harmonic series, right? And it would also share the same characteristic as this one. Or sorry. I'm flipping it around.
Yeah.
Sorry. It's just greater than 1. We don't want, I'm so sorry.
It was 1.
It's just greater than 1. I was still in harmonic mode. I said harmonic earlier, and I was thinking about that, and I shouldn't have been. So 4/3 is bigger than 1. That's the most important thing. So the p-test will then tell us the series does what? Converges, yes. Therefore, that series that we were thinking about converges. And like I said before, I'll instruct you to do this on a quiz or a test. I just want you to mention what you used. So it converges, and the name of the reasoning that you used is the p-test, and that's all you got to have. So you definitely want to positively identify the p-value and its relationship to the important stuff, like the 1, but greater than 1 or less than or equal to 1, and then draw your conclusion based on that, okay? So when you think about work shown, right, so you don't want to just say, hey, converges, p-test. Show the analysis, right? I identified the p-value, here it is, and here's what it means. Here's my conclusion. Okay, we good? Okay, so McKenna, your question from earlier, let's go back to number 3, and I think we can answer this question. Yeah, we can definitely answer this question here. So let's go through the reasoning again. I think that that's really crucial for us to be able to start in the right place. What does the nth term test tell us? Nothing, right? So you're heading towards 0 on the nth term. That just means we learned nothing from the nth term test. Is it geometric?
No.
Nope, it's the wrong pattern for geometric. Is it a p-series?
No.
Almost, right? It's close. If that +1 was gone, then it would definitely be a p-series, and you could just say, hey, p is 2, therefore the series converges, right? But it's not that, and so we're going to have to use the integral test. So we would set this up and say, like we've done before, f of n equals a sub n is positive, continuous, and decreasing on the interval that we are working on, which is 1 to infinity. Therefore, we can use the integral test, and here's what it would look like. We'd go limit as b heads towards infinity of the integral from 1 to b of 1 over n squared plus 1 dn. And again, kind of like that one we did earlier, this might be a good opportunity for you to recall a little bit about some of those integrand forms we've looked at in first semester. Do you guys know where this one's headed? Arctan. Yes, this is arctangent. Nice work. And not only is it arctangent, but there's no adjustments needed like we had before. You know how it was like 1/2 natural log or whatever. This perfectly fits the arctangent pattern right now. So we'd go limit as b goes towards infinity, and it would be arctangent. The notation could be a little weird here. It's arctangent of n, right? Evaluated from 1 to b. And then we do the FTC with this, and we end up with arctan of b minus arctan of 1. So arctangent of 1, that's a real number, right? What angle has a tangent of 1? Pi over 4. So we could just keep that in the back of our minds. Arctangent is really pi over 4. But isn't like the thing this right here, this is the thing we got to figure out. What is the limit as b heads towards infinity of arctangent of b? We've actually done some stuff with this before. Think about the graph. Yeah. That's right. Remember how we looked at the graph? And arctangent, don't write this down unless you really want to. Just try to squeeze it in. Let's try that one more time. Arctangent looks like this, and aren't there horizontal asymptotes? So as you head way to the far right end of the graph, which is what limit as b goes to infinity is telling us to do, we're really describing that horizontal asymptote, the upper one. And I think you're right, McKenna, right? Pi over 2 is where that is. And so you're totally right. We could look at this and say, as I try to evaluate that limit as b goes towards infinity, we could say that it's really, this leads us to pi over 2 minus pi over 4, which is equal to pi over 4. And so pi over 4, that's a real number, isn't it? So that means that that integral, that improper integral, converges, right? So we could say, this is pi over 4 is a real number. I don't think we really need to specify that. We can see it's a real number. So we could say, therefore, the sigma from 1 to infinity of 1 over n squared plus 1 also converges. And the reasoning, of course, the name of the reasoning is the integral test. So McKenna, all the way back around to your question earlier, she was pointing out that in the instructions for the integral test, it said that if the integral converges, then the series also converges, but not necessarily to the same value. And this would be a great case of where we could talk about that. This is what the improper integral converged to, right? So the solution, the evaluation of the improper integral is pi over 4. That does not mean that the series converges to pi over 4. I can explain why real quick graphically. If you think about a series, like if you think about what that graph looks like, 1 over n squared plus 1 looks like kind of looks like this. So remember, a definite integral is simply an infinite summation of super skinny things, right? And so we're going to just be adding up all these little strips of dx super skinny wide, rectangles. That makes sense. Whereas a series is discrete, right? It's like integer values, 1, 2, 3, 4, 5. So you'd be adding up, like when x is 1, when x is 2. So this would almost be like a right sum, right sum. And so you can see that the adding up just the numbers in the series, wouldn't that be skipping all of the numbers in between the 1 and the 2, and the 2 and the 3, and the 3 and the 4? You'd be skipping all those potential inputs that you added up with the integral. And so it's simply saying that just because the integral converged to pi over 4, almost for sure means that the series did not. Does that make sense?
Yeah.
All this will tell us is, the series converges, and that's all we know. We don't really go beyond that. So, okay. Hope you have a great day. Remember to go see Mr. Blake if you are interested.